Greetings and namaste. Today, I will be giving physics lecture number 1. This lecture will be split up into 5 parts. The first part will be about the difference between a model, a theory, and a law. To give you a quick snapshot on this section, I will talk about what is a theory and what is not a theory. So, for example, Aristotle once said that all substances in the world were made of a mix of 5 materials. Earth, which means like rock, stone, dirt, etc., not like the actual earth. Water, fire, air, and ether. However, this is not a theory because it does not allow us to make any other predictions about the world. However, what about Sir Isaac Newton's theory of gravity? Or, to be specific, what about one of his laws of motion, F equals ma? Well, that allows us to make a prediction, specifically maybe some predictions on the motions of the planets in the solar system. So, those predictions make it a theory. So if we cannot make a prediction with the statement, then that statement is not a theory. The second part of our lecture will be about measurement uncertainty. Essentially, that means that you cannot ever make a perfect measurement. So, even when you zoom in more and more, there will always be some kind of error, no matter how much energy you put into it. In fact, when you put enough energy into being as precise as you can, it's just going to create a black hole. So all that effort would have been for nothing. The third part of our lesson will be about precision and accuracy. So, for example, no precision and no accuracy would just be random shots on a dartboard. Precision and accuracy would be a bullseye, but precision and no accuracy would be consistently getting the same shot that are really far away from the bullseye. So, that means that precision and accuracy are not the same thing, and while they are commonly found together, one is not the other, although they are very interchangeable. Now, for my favorite part of the lecture, possibly because you could call it SigFiggies, significant figures, or SigFigs for short. So essentially, what's the difference between 450 and 450.00? While 450 can be rounding, it could be any value from that's above 449.5 and below 450.5. However, 450.00 gives us the specification that the first 2 digits are 00, which makes it more precise, and closer to 450.00000 and so on, our actual perception of the concrete number 450. So, now comes the final part of the lesson, in which we will be talking about orders of magnitude. Orders of magnitude are essentially like powers of 10. So like 2 orders of magnitude times 100, because the 10 to the power of 2 is 100, so on and so forth. They are also related to logarithms, but we'll explore that in a future lesson. Let's dive into section 1, the difference between a model, a theory, and a law.
First of all, what is a model, you might be thinking? A model is something you can use to, model some natural phenomena like an apple falling or a moon orbiting the earth. So, for example, let's say I wanted to, model the moon orbiting the earth. How am I going to do that? I can't just take a rocket and blast off and go to the moon. There must be some way to, model it. And that's exactly what a model is. Now, let's imagine up a model. Let's say that, I had water, and maybe that could be the moon, and then I had my hand, which would be holding a rope connecting to that water. That rope would probably be gravity, and maybe my hand, which is actually smaller than the water apparently, could be earth. Let's try this out. This water, it's real water. You can see it. Now let's see what happens when we drop a coin in it. This is a bucket of water. Now of course you know it'll spill out if I flip it upside down, just like when an apple falls, it's just being pulled to the ground and there's no other force. But here I have this rope, which is gravity, and here I have my hand, which will be earth. I will hold it a little like here. Now I have this model in my mind. So now when I bite, I have this in my mind. When I go to sleep, I have this in my mind. When I wake up, I have it in my mind. So that means that with this, I can formulate a theory. Now, what is a theory? Well, a theory is something that is hypothetically testable. It's a hypothesis that is testable. So it can be clarified right or wrong by some certain experiment. So that's what a theory is. So my theory is that this is almost exactly how the moon orbits the earth. But the thing is, there's no rope between the earth and the moon. At least we can't see it. So what is this rope supposed to suggest? Well, it's gravity, which is kind of like an invisible rope. It's a force pulling two objects together. What is the difference between a traffic law and a physical law? Well, a traffic law is prescriptive. You don't have to follow it. You have physical laws that describe a number of natural phenomena. So now I'm going to use my model of a water bucket and a rope, and I'm going to use my theory that, well, centripetal force, velocity, and gravity are all related in some way to formulate our final equation that is a law, which would be the centripetal force is equal to the mass times velocity squared over r. Because according, there's another law that states because according to our observations, A is equal to v squared over r. And we combine that with the findings of Sir Isaac Newton to get our law. So that's the difference between the model, the theory, and the law. Don't forget to use these three concepts, a model, a theory, and the law, to discover something new and discover something great. We'll be looking at measurement and uncertainty. So now, before we start, I want you to pick up your pen and paper because, well, measurement and uncertainty is going to be a ride, just like all the other physics lectures. So, first let's talk about measurement. So, what is a measurement? Well, let's say you had a centimeter ruler like this one, which measures to 30 centimeters or about 1 foot. And well, if you measure something like 30 centimeters, alright, so far so good. And then we get 60, that's a crack. Jesus Christ, that's not good at 56 centimeters. Anyways, now we are going to be looking at 90 centimeters. Don't let the ant crawl on me. And then we have 120 centimeters. Good so far. And then we have 150 centimeters. And then I guess 180 centimeters, almost 200. Then we get 210 centimeters. And then you get 240 centimeters. Now I measured this bench to be 240 centimeters in length, but my ruler was only accurate up to about 0.1 centimeters. Plus my own error with my little hands probably accounts for a part of that too. You can never, absolutely never, get a perfect measurement. And here's why. You know that bench over there? Well, that was 240 centimeters about. But the reason I say about is that because of our ruler only measures up to 0.1 centimeters of accuracy. And plus, there's probably some inaccuracy on my own little fingers trying to measure where it last stopped. So, it's probably lying plus minus 0.2 centimeters or something like that. So, it must be lying somewhere between, well, 239.8 and 240.2. It gotta be somewhere there, right? Now, the thing is, even if you take some digital perfect ruler and try to measure an object using that, you can only get down to 1 Planck length, which no doubt is incredibly small, smaller than even some quarks. But the thing is, the Planck length is bigger than a singularity, meaning that we cannot ever measure to the perfect degree. That's called the principle of uncertainty. Uncertainty means you'll never actually be able to measure something. But how close can we get there? Well, let's say we have precision and we have accuracy. Two wildly different things that people still misconceptualize as the same thing, which is honestly confusing nowadays, because precision and accuracy are wildly different, although they can be synonymous in some scenarios. Anyways, what is the thing that differs from precision and accuracy? Let's say that we have a dartboard to visualize precision and accuracy. And now, let's say I have 4 shots on all of them. So, let's say that I want high precision but low accuracy. High precision but low accuracy. How can this turn out? Well, high precision means you're getting consistent, but low accuracy means you're nowhere near the true value. So that means that, you get something, since the only component is precision here, and there's almost no accuracy, you get consistent results every time. They're far from the true answer, but they're consistent. That means they always are near each other every time. Just do that with the bullseye, and then you're the best player ever. They kind of go together. It's going to be hard to explain. But basically, you're getting near a bullseye, so you're close to the true value, but your answers themselves are pretty far away from each other. So they're not that consistent, although they're scoring near the bullseye. They're not that consistent. So that means that although there's high accuracy, there's very low precision. That means that, this is basically how it would look like. But now, let's become the worst, laziest player of darts that you could ever freaking get. Low precision, low accuracy. What is this gonna be? Well, it's certainly not gonna be this. How about we sit on the couch and shoot at the wall? So, you just shoot at the wall. Now, they're nowhere close to the bullseye. They're not even on the board anymore. And they're not even consistent at all. So this isn't really that close to this. It takes an entire bullseye stretching between them. Then you have this. Yeah, you can see they're not that consistent. I'll just tell you that much. Now, high precision and high accuracy. Accuracy would mean getting near a true value. So let's use green for that. So getting near the true value would be getting near a bullseye. And precision would be getting consistent results. In this case, consistent results near a bullseye, because we're aiming for the true value, which is a bullseye. So, you would basically just get a bullseye every time. Nice, am I right? Earlier, that bench I measured to be 240 centimeters. But I don't know. This could have probably been an error on my part. There's probably some degree of uncertainty, since it only went up to 1 centimeter as the smallest division. So that means that it's probably the answer is actually plus minus 1 centimeter. It could range anywhere from 239 to 241 centimeters. And that, folks, is how you take care of uncertainty. To find the percent error is we divide 2% by the measurement that we made, notably 240 centimeters, and multiply it by 100%. Now, after doing some of the maths and doing some of the hacks on my computer, I can calculate that it's about, let me think for a second. So we are dividing 2%, which would be 0.02. Well, let's just think of it as 200, and then we're dividing it by 240, 5/6%. So that's a very small error, but it's still error. So that means that it's uncertain. What we learned is, some things just can't be trusted, like your scale. your scale puts unreliable numbers when it puts the second decimal digit when it knows it can't even measure the second decimal digit. So is that really a significant figure? And that, folks, leads us to SigFigs. Now let's just go all the way back to the previous lesson, uncertainty for this one. Now, during uncertainty, I was actually lying to you. You remember that bench I measured for you? 240 centimeters? Well, I actually made an intentional mistake over there. It wasn't 240 centimeters. And I gave you 24 hours to find it. This lesson, I'm going to fix my intentional mistake, and you'll get that answer key. Alright. So, what was my mistake?
240 centimeters was wrong. So, what was right? Gave you 24 hours to figure it out. And, well, which one is right? Shut up, you! We don't need you around. But anyways, which one was the right measurement? Hint, hint, one of them is already wrong. I already narrowed the chances down to 33.333. Okay, I'm not a calculator. Not going to infinitely input that much crap. But anyways, what's the length of that bench? Well, is it A? No. Is it B? Also no. Is it C? Also no. But is it D? Yes, yes, and yes. Now, if vision is not your strongest suit, then you might be asking, what's the difference between A and D? Well, it's this little dot right over here. And what does that dot mean? Well, that's exactly what we're going to explore today. So, today we will be looking at SigFig. 3 SigFigs. Alright. Now, what's the second rule? That you had, 6 million. I think that's 6 million. But anyways, how many SigFigs does this have? Just one. Why? Well, because these trailing zeros, we don't know what they are. This is just an estimate. This, 100,000th place could be something other than 0. We can't assume. And thus, we only know one reliable digit, or only one digit actually contributes to our measurement. And so, there's only one SigFig. I don't know why I wrote the plural S. Sorry, the noggin isn't working. Anyways, number 3. Leading zeros are not SigFigs either. Wait, why did I put that? Aren't SigFigs. SigFigs. Jeez. Oh, jeez. Oh, nice. Alright. Leading zeros aren't SigFigs. For example, 0.67. Oh, well, actually, let's be more creative and put 0.65. So, how many SigFigs does this have? This very, very creative number that isn't just a sequence of 2 numbers have. Well, it would only have 2. Why? Well, 1, 2. This, the leading zero, is not a SigFig because we don't know what that ones place could be. So there are only 2 SigFigs, 6 and 5. Number 4, and this is kind of like a subset of rule 2 and 3, and this is kind of an exception. But trapped zeros count as SigFigs. So, for example, you have, this actually is the thing that covers that first choice at the beginning. Your D is correct because of this rule. So, for example, 606 or error 404 may be nostalgic to you people who were born in the 90s and always saw Windows and the internet crashing. But anyways, these zeros in the middle that are sandwiched, we know what their value is. They're assured because, first of all,
there's something that's preventing them from being a trailing zero, and there's another thing preventing them from being a leading zero. And thus, by convention, this must be the known value of, our tens place. Our tens place must be 0 if the 0 number is sandwiched between two things. So, likewise, let's say that we weren't sandwiched by a number, but by a decimal point. Dun-dun-dun. So, let's say we have 70. 70 by itself just has one trailing zero, meaning that doesn't contribute to the measurement. But remember that thing that made the entire difference between life and death. I mean, not life and death, just correct and wrong measurement, was the decimal point. That decimal point is just like a phantom number. It's like a ghost number. It doesn't actually, do anything for the measurement, but it's something that sandwiches the zero. Oh my freaking god, why did I switch the highlighter? It's something that sandwiches the zero and doesn't allow it to be a trailing zero either. So this stops the zero from being a trailing zero and gives it some value. If we put this but no number after it, we know that our tens place, which is the number directly after it, is left ambiguous. But we know for sure that the ones place is 0. That's what made the difference between, wrong and correct measurement. The thing is, in addition, let's say that you have 6. Sure! Sorry, he's just being a little wobbly right now. Alright, so 6.65, and then let's say you add that to 5.5. Now, if you were in the perfect world of pure math, you would probably just say, hey, I think this is 12.15 because I'm smart. But you're wrong, because this only has 2 SigFigs, while this has 3. So the final answer must only have 2 SigFigs. See, now you're thinking like a smart man mathematician. And so this can't be 12.15, but it's 12. Dot. So subtraction 0.5. Now the smart mathematicians out there might be saying again, 5.05. But wrong. That's all wrong. How is it wrong? Well, that's because 2.5 only has 2 SigFigs, while 7.55 has 3. There could be anything lying beyond that 5. So that means that the final answer would not be 5.05, as the smarty mathematicians would say, but rather it would be rounding up to 5.1. 2 SigFigs. Multiplication, 32 times 25 is 800. So now, 3.2 times 2.5. All the smarty math-men out here would say again, I ate this problem. I tried to make a joke with aced. But anyways, it would say 8. But 8 is wrong. Why? Well, you see, 1 SigFig, 2 SigFigs on this one, 2 SigFigs on this one, but why 1 SigFig on this one? We're not dividing SigFigs, are we? So, we must have 2 SigFigs in our answer. And that means the mathy smarty men didn't add something this time. They missed something. So, the answer is actually 8.0, at least in physics. So now, finally, we got to division. A, 0.7, that's wrong. Lazios. B, 0.67. And then 0.6666666. Well, in the world of mathy, this would be right because 2 and 3 are perfect, but they're wrong. It was a shameless plug. But anyways, 0.67. Finally, B. That's correct. Because remember, this leading zero, not a factor, not a SigFig. So, that means that there's only 2 SigFigs when there must be 2. And, well, the answer... Geez, I'm really getting tired. Sorry. Well, anyways, let's go
So with exponents, let's say you have 5.4 scientific notations together, they should give you an answer with 2 SigFiggies. So, sorry folks, so 5.4 times 10 to the 3 plus 2.1 times 10 to the 4th. A normal mathematician would put it as, I am smart. 0.54 times 10 to the 4th plus 2.1 times 10 to the 4th. And that's another mathematician offended. Moving on. So, that gives us, 2.64 times 10 to the 4th. But that's only in the magical, perfect world of mathematics. The cameraman looks literally dead inside. But anyways, what about in the non-perfect, non-surreal world of physics? Well, in the non-perfect, non-surreal world of physics, we only know for sure this tens digit. We don't know what the hundredths digit is, so why bother to include it in the measurement? So, that means that if you were actually doing it in physics, our answer would only have 2 SigFiggies, 2.6 times 10 to the 4th. So that's the real answer. What about angles? So, angles are the final terror here. Have any decimal points or anything. So, why bother including more than 2 SigFigs? So, all the calculators would give you this givers, but that's only because they're designed for math. If you were doing physics, you would just use 0.87 when you're using realistic SigFigs. We will be looking at orders of magnitude. Now, SigFiggies, the whole deal with SigFiggies was cramming in as much accuracy as possible without making any assumptions. But, orders of magnitude are almost the exact opposite. The definition of an order of magnitude just a sheer estimate, and it can only have 1 SigFig at most. 1 SigFig. Now, the mathematical definition would be, powers of 10. What you should know if you study scientific notation, wink wink, future lesson. But the thing is, they are just used for sheer estimates, and they're nowhere near accurate. But if you don't have enough data, this is very reasonable to use. If you do have a lot of data though, can use more than 1 SigFig, then why would you be using this? But this is just if you don't have enough data, which is very important and actually very common when you're studying things in science. So I have the giant lake all the way behind me. You can probably see it if I move a little. We'll capture the lake. You can probably see it. And now let's say I want to measure the volume of this lake. Measuring. Professor Suborno.exe, he fainted. Oh, sorry. The thing is, I can't just measure it with my eyes. I can't eyeball it this time. But the thing is, instead, have to use a model, because nobody's going to take some 15-gallon water bottle out of nowhere, pour everything out, and then just swallow this entire lake up. If you have a 15-gallon cup in the comments, please tell me. I'll make sure to buy it, no matter what price you set. I want to capture all this water. But anyways, the thing is, how are we going to find it? Well, we need some sort of estimate. But the thing is, we can't use any SigFiggies. So what can we use? The order of magnitude model can we use to measure this lake? Well, let's give you 6 choices. You have square, circle, quack, triangle, cube, rectangular prism, and cylinder. Now, I want you to find the correct answer for all 7. Now the duck keeps suggesting that the answer is quack. But is it really quack? No, I'm sorry, the 7th option is wrong. So what is the answer to this? What model should we use for this lake? Well, of course, the lake is 3D, it has some depth. So circle, square, triangle, quack, they're all pieces of leaf. So now we only have 3 choices left. Let's raise the suspense. Okay, this drum roll with my legs is probably not a good idea. But anyways, we have a cube, a rectangular prism, and the cylinder left. Now obviously, this is not rectangular in the slightest. You can just observe for a second and tell me if it's rectangular.
That damn plane up there! Okay, sorry. But anyways, this is not rectangular or square in the slightest. The surface of this is not rectangular or square. Now you can see that lake behind me is not rectangular or square in the slightest. Now it's not quite circular either because of that little panhandle over there. But the thing is, the circular, the closest thing we can get. That means that is the best model. Not crack, not a rectangular prism or a cube. And that means that we should use a cylinder. So, oh my god. Hi, verb. Alright, so now the cracker has passed. But anyways, what can we use to measure this? So, well, let's say that this is about 1 kilometer long. Let's go to the smartboard and get this done. We will be estimating the volume of water in this lake. Of course, according to my observations, the water looked like this. It looked like this. And this area was covered in lily pads. But still, this is approximately how it looked like, which is nowhere near a circle. We would have to cut off the nose if we do. But the thing is, a cylinder or a circle base is the best we can get. And obviously, there's going to be different depth because I saw like the edge of it was just inches long. It was really shallow at the edges, but really deep. So if we were talking real, we would be probably talking half of a sphere or semi-sphere or a hemisphere, sorry. But we're talking just an estimate. So we'll be looking at a cylinder. That's a very sloppy cylinder. Now, of course, a cylinder's area is pi r squared 8. What would be the length or the diameter of this lake? Well, that would be equal to 1 kilometer, at least according to my estimate. But for those of you who measure in freedom per square eagle, I know quite a few of my viewers do that. That would be 0.62131 miles. How many SigFig is that? 1, 2, 3, 4, 5. This leading zero is not a SigFig. You can learn this and more in my previous lecture about physics. Hint, click, hint, click, click. But anyways, that's our length. But we need to cut it in half. So, just like the Roman Empire, we're going to slice it in half, giving us a nice and clean 500 meters. That's not a 5. Alright, let's write the equation for the volume. So volume is pi times 500 whole squared, 500 meters whole squared. Can't forget the units. And then you have h, and that would be, let's say that we have times 100. Actually, I said 100 in the video, but well, let's just pretend it never existed. It's out of existence. Just like the Ingsoc papers in 1984. They don't need to know. But anyways, don't tell the viewers past this point that I actually said 100 meters. It was actually just 10 meters all along. They don't do that in Western China anymore. But anyways, it was out of existence. But anyways, that gives us v equals, for disrespect, 3. Just like in communist Russia, everyone is equal. Even the pi. 3. So times 500 squared, calculating 25000. So now let's put the meter squared, and then we have the 10 meters. Wow. Now we're simplifying it. So now that gives us 3 times 2.5 times 10 to the 5th. But remember, we have an extra 10. So that gives us 10 to the 6th. Jesus Christ, we have fatty numbers over here. But then, meter cubed. But where the m squared and m into this one. But anyways, sorry. Now this is on the upper side of the caste system. I mean, this is on the upper side of the spectrum from 1 to 10. And so that gives us, well, let's estimate, to the order of magnitude of 7. That gives us 10 to the 7th power. 2. Drum roll, please. That wasn't a drum roll. That was a leg roll. But anyways, 10 to the 7th power. Meter cubed. Okay, I gotta go.
to Bari Science Lab to fall in love with math and science, especially programming.